Good morning, everyone, and welcome to today's webinar covering case studies using Zeolite to treat AMD and metal-contaminated waters. So presenting today is Dan Ide, CTO and President of St. Cloud Mining Company, and I'm Barbara Carroll with Geographics GIS Services. Right now, I'd like to introduce Dan Ide of St. Cloud Mining Company. Dan?
Well, thanks everyone for coming today. I'd like to thank Barbara for the hard work she's put into getting this presentation together, and also Tiff Hilton, who has taken the time to share a lot of the information that we have in the presentation. During the presentation, if there's other sources of information, I'll acknowledge those individuals as well. We'll go ahead and get started. All right, today we're going to cover 7 general areas. The first is, what are zeolites? As the largest producer of zeolite minerals in the U.S. and probably the Western Hemisphere, we should be able to give you a reasonable explanation. We're going to talk about different large-scale projects that zeolites have been used in, and then we're going to go through 4 case studies, one in West Virginia, one in Grants, New Mexico, which is uranium, leaking uranium site at Homestakes, the C.R. Kendall thallium operations in Helger, Montana, where they're controlled gold mining operation that's has a thallium discharge, and finally the Lead Queen mine passive treatment system that's being installed in Patagonia, Arizona, that for all intents and purposes resembles on a much smaller scale what happened along the Animas River in Colorado, New Mexico, Utah, and Arizona. And then finally we'll take questions. Okay, what are zeolites? Zeolites are hydrated aluminosilicate minerals. They're what's called a framework structure, and as you can see on your screen, they have large channels running through them that are very evenly sized. These channels are what makes them valuable, and they're used commercially for several reasons. One is they have unique adsorption properties. These channels that you see here, okay, it has large channels that you can see that are evenly sized. This gives them unique absorption properties. Within these channels, they have cations that are naturally there. They're usually things like calcium, sodium, potassium, and magnesium. And these cations can be exchanged for other things in your water effluent that you want to get rid of, like silver, copper, lead, zinc, cesium, strontium, and a bunch of other nasty, thallium. They have the ability to act as a molecular sieve, and that just means that on an angstrom level, they can separate one type, usually of an organic compound, from another. In the case of zeolites, usually it's a straight chain hydrocarbon from a branch chain. The straight chain can go through the channels of the zeolite. The branch, an arm sticks out, gets caught, and a separation of different molecules is made at that point. Finally, they have catalytic abilities. That means that within the channels, either naturally or by adding different types of metals like platinum, vanadium, reactants, these channels can instigate strong chemical reactions that change the character of the material that they're in contact. So they can make different compounds out of mixtures or gases or things inside the zeolite itself. What we're going to talk today are different zeolite-based media systems, and that's just zeolites that are used to remove different types of effluents from or different types of contaminants from effluents, and in our case today we're going to talk primarily about mine waters. And the reason you do this is because zeolites are readily available. The resources of natural zeolites are large, they're well tested, and they're consistent in their performance, and they're also economical. Next, there's a number of commercial technologies where we can improve the selectivity of the zeolite for specific contaminants. We make modifications to zeolites by adding things like surfactants. If we want to take organic contaminants out of water, we can add different metal compounds like iron. A company called WRT uses our clientellite, makes an iron modified product or a modified product to take out a variety of low-level radioactive contaminants like thallium, thorium, radium, uranium, things like that. And then we can change it, for example, a different way to make the zeolite very selective based on size for things like ammonia, even in the presence of what would normally be a cation calcium. So we can take ammonia out of difficult effluents that have high concentrations of calcium and still retain the efficacy of the product. The technology is proven in municipal and drinking water applications, nuclear and industrial water treatment applications, and we're seeing that we're finally getting some traction into mine polishing type of applications prior to discharge. There's a lot of really good commercial treatment technologies out there, but as states and the federal government continue to lower the allowable discharge, those technologies can no longer get there, and the zeolites work very well at polishing the material at that point. Where are they used? I've just said here's a series of things that we've worked on over the recent past that are large zeolite treatment projects. Not so recent past was the first one I worked on as a consultant at the time to Union Carbide, and that was 3 Mile Island. So I started my career with the first really big pit at Bowie, Arizona, and the zeolite went from Union Carbide to 3 Mile Island to treat primarily cesium and strontium in water that was in the containment vessel of the reactor and inside the contaminated facility. And a lot of the techniques that were later used in Fukushima were developed in this test area or treatment area. The Kendall mine that we'll talk about later, thallium, copper, lead, zinc, cobalt. The Homestake Legacy site, Grants, New Mexico, is primarily uranium. The Colorado tailings, we did a test with Montana Mines, copper, lead, zinc, silver. It didn't go, unfortunately, past the pilot. The Greenbrier coal operation in West Virginia, the work that Tiff Hilton did, AMD, manganese, aluminum, and the series of pilots, and now we're working to build on that technology. A partner company, Rimcon, also used the zeolites in Wyoming to mitigate high sodic waters. WRT, also a partner company, has over 100 commercial installations across the United States to remove arsenic, radium, thorium, uranium from municipal drinking water. And then finally, the big project that started in 2011 with us and the partner company Curion, we removed cesium, strontium, americium, calcium using zeolites on the treatment. Primarily, the target was cesium. And the material that Curion supplied did a lot of the early heavy lifting on the removal of zeolites or removal of contaminants from the effluent streams outside. We'll go to case one. And that's the West Virginia coal mine water discharge. The individual that did all the work here was a guy named Tiff Hilton, and we're also working on some additional projects with Thomas Cook of Navigator. Basically, the issues that we wanted to resolve were AMD, which is acid mine drainage, and that's because a lot of the discharge mining waters from coal operations can be extremely low. We wanted to see what we could do with manganese, which is a common problem at the lower effluent levels, dissolved aluminum, iron, turbidity, and TDS. Next. Just to give you an idea where the Greenbrier operations are, to the right center of the page you see the 4 operations, Brown Creek, Buck Lily, Point Mountain, and Midland 2. They're in Greenbrier County and just to the east of Rupert, West Virginia. Brown Creek, typical large-scale open pit mine. Almost all these mining operations anymore in the southeast have very good control of their water. So what we were doing is taking different point sources or and it was different at each operation, but TIFF laid out a series of pilot scale zeolite things that tested the discharge water, and we then saw what we could do on a pilot scale basis. Go ahead, Barb. Buck Lily, again, Midland 2, and Point Mountain. And the first thing we wanted to figure out from the West Virginia testing was, do zeolites do anything? So basically, when I say we, TIFF collected a series of raw water analyses. There's 3 samples listed, and you can see the pH on all of them is very low. The dissolved iron goes from low to fairly high. The dissolved manganese was clearly out of specification, as is the dissolved aluminum. And what were the results? When we contacted the water with the zeolites, what we saw in all 3 cases was a significant increase in pH. It didn't get us all the way to a 6, where you begin to get reestablishment of different types of aquatic life, but it typically raised the water content by almost 2.5 to 3 pH points. In addition, it reduced the iron significantly, it reduced the manganese significantly, and it reduced the dissolved aluminum down to discharge level. Next question is, given that we probably weren't going to start with raw water, we were going to end up dealing with waters that had been treated prior to sampling. So we looked at 2 things. One is we looked at water that was AMD water that had been treated with sodium hydroxide, followed by a zeolite treatment, and then water that had been treated with lime, followed by a zeolite treatment. And once again, we saw buffering, but we saw it in the other direction. And if you go across on the first line, we raised the pH from 3.45 up to 10.89, but in contact with the zeolite, we drove the water down. We buffered it to a lower pH. And you saw the same thing happening with calcium. And then as you went down and looked at what happened to the iron, well, we didn't make a huge impact there. The iron was already gone. But the dissolved manganese, typical of the water treatment got it. The big effect there was what happened to the aluminum, which was one of the difficult areas. And then finally, you saw that on TDS, it looks like we typically reduced it by a third. The question is, how do you get something from an idea into a process? And TIFF gave me the original napkin on which they sketched out the original thoughts of how you've made a treatment process. We ultimately tried it a couple different ways. One is the simple way of taking the zeolites as it arrives in a super bag, putting it in a cage that you'd normally hold large containers of chemicals in to give it structure, and then run the water through it in a downflow mode on a very simple system. Second way was actually to take the design and say, can we catch the water and build some sort of a treatment system that allows the water to go through the zeolite, in this case, over, come back up, go over and down, and then finally discharge. And this is an actual installation of the treatment water at one of the operations there in West Virginia. The second case study is what happens on a large-scale treatment study for uranium. And this is actually being currently installed. There were 3 steps. There was an additional 100-ton pilot study that was done by RIMCON, followed by a 1,000-ton pilot study where you really began to test the limits of the system. And then finally, the final system's being installed, and it took almost 5,000 tons of zeolites. Basically, what we were treating was a uranium processing facility. It was built in 1958 on a remote ranch plant. It was operated by Homestake through the 90s and has been presently inactive. except for the remediation that started in 1977. Not a lot happened until June 2007 when New Mexico lowered its state standard down to the EPA standard. They went from 5,000 ppb to 30 ppb. They started out using reverse osmosis to augment the groundwater clean activities, and then the brine from the RO, or the reject water, was put into evaporation problems. Then they started testing the zeolite to treat the low concentrations of uranium-contaminated water from the upper Chenli, and then that water was re-injected. The entire system, like I said, was just designed by Rimcon LLC, Dale Shea. This just shows the grant site, and I was actually up there a couple weekends ago and took a look at it, and it's pretty interesting. You've got a large, almost east-west tailings pile, and the zeolites are treatment areas put up on top, and then the RO treatment system is to the far west side of the operation. What we were doing, and when you're picking the water out, is you can see that the tailings pond is in the upper right-hand corner, and it just says large tailings pile, and it's a topographic high, and you can see that the uranium plume has come out and contaminated the groundwater below, and they monitor it by testing. And I drove all through that area, and they have monitor wells all over the place. Looking at the operation cross-section, these wells, there were 3 different aquifers, and what we were treating was the middle Chenli formation, the one that's in red in the middle, and the water's pumped up and run through the zeolites and then discharged later. You can see the design area in the back. The zeolites were built in the large cells, placed in large cells. They can take the water at close to, I think it's 300 or 450 gallons per minute, and they have, I believe it's 4 trains. It can treat a total of about 1,250 gallons per minute. They use a 14 by 40 mesh zeolite product we produce from our Winston operation. The brief update is that the original pilot scale of 1,000 tons worked as designed, and they're nearly done with the large-scale system. They have the permitting and regulatory approvals received, and the full-scale installation will be completed towards the end of this year, and then they'll be up and running. I've included the information for contacting Dale Shea, the individual that came up with the treatment scheme. His company is Rimcon LLC. Case 3 discusses thallium removal at the C.R. Kindle gold mine in Hilger mine in Montana. Basically, it was an open cast gold mine. They went through a series of sediments that had some low levels of thallium in them. Montana has lowered their discharge standards down to a discharge of no more than 1.7 ppb. Unfortunately, we can't get consistent laboratory testing to give us a number any better than less than 2. But they put in a fairly nice treatment system. The original system was a series of this is just a location map of where the operation is in relation to Montana. It's in basically central Montana. The C.R. Kindle mine is a RCRA site, and they had to file a fairly complete treatment plan on this thing. So the data is not confidential. It's taken from the treatment plan so that you can follow this stuff and see how the operation works. The Kindle pit, and we've been supplying zeolites first from my company GSA, second from another company I worked with, and finally the same zeolite from the St. Cloud Mining Company. And this treatment facility has been in operation since 1998. Okay, back to the treatment system. Basically, they had to use things that were on site. The original test thing was a series of zeolite columns that were upflown. The overflow went into the next column, went down and then upflowed through a series of columns. And the idea was to, at the end of the column, have zero discharge for all intents and purposes of thallium, and then be able to add columns at the front of the system as the zeolite in the back of the system was completely inundated and could take no more thallium, so that they got full use of the zeolite. Just looking more closely at the profile. The reason they use an upflow system at this facility was that they had water from a variety of sources, and what they didn't want to deal with was a capping or a filtration kind of a problem. So if you had debris and leaves and gravel or about anything that could get into that water, because there were real changes through the year of how much water flow came through and what kind of sediment load it could carry, that just simply got trapped in the zeolite upflow system, but did not impact the ability of the zeolite to work well. And this is what this is the pilot system that was originally put in place at the Sierra Kindle mine. Basically, here's what happened. If you look at the orange scale, and I don't know if my thing is showing you, you can see what their influent coming into the zeolite column was. And it varied with time and the amount of gallons that were going through the system. And then what would happen was there's almost no zeolite coming out of the first column. And then over time, you get to the point where influent equals effluent, and the zeolite, for all intents and purposes, is exhausted at that point. But the water is now going into column 2, and the same thing happens over and over all through all of the systems. At the very end, basically on the pilot scale, they got to 1 million gallons almost of discharge without any thallium for coming out of the effluent. And this system finally went to a full-scale system that's been in place for years and years. This was work done in the late 90s, 1998, I believe, through early 2000. And once again, you can just look at the zeolite column and see what's going on in a little bit closer things. You have high levels of effluent coming in. The first column comes in contact with it. You start to get breakthrough at some point, but the water is still going through the second column, going through the third column, going through the fourth column, and finally going through the last column. But we're staying below the discharge level of required by their MPDES permit. The question is, once you've loaded the zeolite on something, what happens? And they did the TCLP tests, and basically what went on to the zeolite stayed on the zeolite. So the zeolite was able to be disposed on site in a lined area for long-term disposal. The final case is in southern Arizona. We had originally gone to the state of Arizona on a proposal or a request for proposal and said, look, we want to treat these sites. Here's the problems. There's high pH in the drainage waters. We need or low pH in the drainage waters. We need to raise it, and then we need to get the different types of metals out of the zeolites, and here's the plan that we have to get these things out. So we had basically a passive system on an old mining area in southern Arizona. Project area is darn near on the U.S.-Mexican border. It's near the Red Mountain porphyry copper deposit discovered by Kerr-McGee's in the late 70s, early 80s. And what we were trying to do was deal with some of the legacy mining that was in the area, and there was a series of watersheds that had this low pH waters. The waters came out of these areas intermittently. There wasn't usually a flow year-round, but some parts of the year there were very high flows, and then for most of the year there was some flow, and all the water ended up went through a very pristine riparian area further down along the drainages and into Patagonia Lake. The reasons to do this project is that they had done a series of remedial actions where they covered the tailings, they closed portals, and all these things, but didn't really solve the problem. So the idea was, could we put in something passively that would work on this project? And the original goal of this project was, as we proposed to the state, was deal with these drainages in red and get these things going. The geology of the area was such that it wasn't really acid mine drainage as much as it was acid rock drainage. The big porphyry had come up into the area, and whether or not mining had ever been done in the area, the waters of that was going in those drainages was going to be very low in pH. In addition, though, there was metals that were there, and you can see some of the waters or some of the effluents that were coming off. It was pH of 2.6. It had very high levels of sulfate, high levels of iron. I mean, it's kind of a nasty effluent. And let's just say that we believed we had a solution. And the geology was such that we were trying to figure a way to resolve this thing, and we looked at the concept of kind of passive barriers in different types of streams. So we were using a model of gabion walls or gabion dams containing zeolites, or holding a bed of zeolites behind them. And what we couldn't deal with was just the fact that there were all these structures out there, so we just had to be able to locate in the streams where the water came back to the surface and expressed itself. We couldn't do anything, of course, about the groundwater below. The contaminants express themselves as salts that would dry out when the water level got low, and when the water level got high again, immediately dissolve and load up the stream. And you saw these metal salt deposits all through the area. Basically, what we had to deal with was the idea there was about 86 pounds of combined metals coming downstream each month, and could we make an impact on that? The model that we came up with is a series of gabion dams, and the dams held the water just long enough for the water to back up into the zeolite beds, and then came through the gabion dam over and through a sentinel core that had zeolites and discharged out into a second bed that's in front of the Gabion Dam. So what we propose to the state is, look, we'll set up out there and we'll test the water on an ongoing basis and show that we have improvement. And this was a proposal that was submitted to the state of Arizona. And unfortunately, we've got to something where I left something out of the slideshow. What happened was that the state of Arizona said, no, that's not going to work. And then we had the great flood in last year. At the end of the year, we had the hurricane come, and what happened was I was sitting in the Pittsburgh airport reading whatever the Pittsburgh paper is, and saw this massive yellow streak going down this thing. It says mining operation, or the Lead Queen mine in Arizona. Immediately recognized where we were and what a mess was there, and it was a giant surprise. And it looked just like Animus, only on a much smaller scale. And what had happened was that the water had gone up over and filled a shaft, and it was like a plumbing deal. As the shaft filled up, there was an adit that was at a little higher elevation but had a hydraulic connection. The water filled the major shaft, unplugged the adit, and pushed an enormous volume of material downstream, creating a huge yellow scar going across the southern Arizona desert, and blam. Immediately the EPA decided that that had to be fixed, and we put a proposal in, or the proposal went into the Forest Service. They took the work we'd done for the state, and that is currently being implemented.
All right. Dan, do you have anything else that you'd like to say before we thank people for attending?
No, I mean, basically, thanks for spending the time to come out here and listen to me. I'm very pleased that a number of you were interested and could take the time. My contact information is up on the screen. Feel free to contact me if you've got any questions, or send me an email.
All right. On behalf of St. Cloud Mining and Dan Ide, I'd like to thank everyone for joining us today, and have a great rest of your day.